Bismillahirrahmanirrahim. In last lecture, we have started a fuel cell. We have learned about the introduction of the fuel cell. That fuel cell is an electrochemical cell. We have determined the difference between fuel cell and heat engine, and we have also compared fuel cell with battery. We have also learned about the Faraday law, which is applicable to any electrochemical cell. So Faraday law is also applicable to the fuel cell. Now in this lecture we will discuss about the utilization of reactant and the stoichiometric ratio, and we will do some problems related to Faraday law. Measure of reactant utilization efficiency. One type of efficiency for a purely electrochemical reaction is based on species consumption. We supply species in pure electrochemical reaction, as we have seen in fuel cell, that we continuously supply hydrogen and oxygen. So the supply of hydrogen and oxygen is basically the species consumption, and the efficiency of electrochemical reaction depends on the species consumption. We have learned from the Faraday law that there will be a minimum amount of reactant required for a given reaction. From Faraday law, we have learned that for any required current, there should be a minimum number of reactant required. So there should be some minimum amount required in order to generate a particular amount of current. In practice, we do not constrain to provide exactly the minimum amount, because there will be some mass losses occur if we provide exactly the minimum amount of reactant. We always provide more than minimum amount of reactant. For a given current, there is a calculated minimum amount of reactant, but there is no maximum limit. For any current, we can calculate the minimum amount of reactant required from a Faraday law, whose equation is written on your screen, but there is no maximum requirement. We can supply a huge amount of reactant, but there is no limit for maximum side. But there is a limit for maximum side, and the minimum amount of reactant is given by Faraday law. The actual flow rate of reactant is a function of pumps and blowers that are used for reactant delivery. Both hydrogen and oxygen are gases, and we use blowers or any other pumping device for the reactant delivery. So the actual flow rate of reactant is basically the function of pump and blower. More high power pumping device will result in high flow rate of the reactant. But if we supply high side reactant, means we are supplying more reactant, then more flow delivered, the higher the parasitic power required. So we generally seek to deliver something close to the minimum requirement. If we supply tremendous amount of hydrogen and oxygen to a particular fuel cell, then it will require a pumping device. And if we require to pump more hydrogen and oxygen, then it will ultimately result in higher pumping power, which ultimately increases the parasitic power, which is the power consumed in order to generate useful power. So generally we deliver power which is closer to the minimum requirement. For this case, we define a Faradic efficiency. Faradic efficiency is a measure of the percent utilization of a reactant in a galvanic process. Faradic efficiency determines how much reactant is utilized in a particular galvanic process. For example, we have supply a particular rate of reactant, it is, and there is theoretical rate required for a reaction. Theoretical required rate of reactant supply is determined from the Faraday law. So the ratio of theoretical rate required for a electrochemical reaction divided by the actual rate of reactant supply is called Faraday efficiency. It determines how much reactant is consumed in order to generate a particular amount of current. We supply a sufficient amount of reactant, and from sufficient amount it might be possible that 100% reactant is consumed in order to generate current, but we have discussed that normally we supply reactant more than the minimum requirement. So Faraday efficiency is basically a measure of percentage utilization, that how much reactant is consumed from the actual rate when to generate a particular amount of current. Faraday efficiency is basically the theoretical required rate of reactant supply. It means that how much effectively reactant will be consumed in order to generate a particular amount of current. Faraday efficiency is often called the fuel utilization efficiency when applied to the fuel in galvanic redox reaction. It is also called fuel utilization efficiency, and it is nothing but the theoretical rate of fuel supplied divided by the actual rate of fuel supplied. Theoretical rate of fuel supplied means the theoretical amount of hydrogen required in order to produce a sufficient amount of current divided by the actual rate of hydrogen supply, and what actual amount of hydrogen we are supplying to generate a particular amount of current. So this is the Faraday efficiency or fuel utilization efficiency. Now we are moving towards another concept, which is the stoichiometric ratio. It is same as we have learned in internal combustion engine. In fuel cell parlance, the term stoichiometric is defined as the inverse of the Faraday efficiency. We have learned air fuel ratio in fuels in heat engine. It is similar to that concept. Stoichiometry is basically the inverse of Faraday efficiency, and it is basically the, if we talk about stoichiometry at cathode, then it will be the actual rate of oxidizer delivered to the cathode divided by the theoretical rate of oxidizer required. What actual amount of oxidizer we are providing at cathode divided by the minimum amount of oxidizer required in order to generate a particular amount of current. This is basically the cathodic stoichiometry. If we talk about anodic stoichiometry, then we know that at anode hydrogen is a fuel and we supply hydrogen at anode. So that's why in anode stoichiometry there is a actual rate of fuel delivered to the anode divided by the theoretical rate of fuel required. Actual fuels amount that we are supplying for power generation divided by the minimum amount of fuel required from the uh, Faraday law. So basically, stoichiometry and Faraday efficiency are inverse of each other, and it determines the parasitic power of the system. We will learn what is basically the parasitic power. Now we are looking for a problem. Consider a single hydrogen fuel cell at 4 ampere current output. We have a fuel cell whose capacity is to generate 4 ampere current. Anode oxidation reaction is H2 will be break down into two electron negative plus 2 H positive. Cathode reduction will be 4 electron negative plus 4 H positive plus O2 H2O, and overall reaction will be H2 plus half O2, and it gives us water. Now, for 4 ampere fuel cell in part A, what is the molar rate of H2 consumed for the electrochemical reaction? What is the part B? What is the molar flow rate of oxygen consumed for the electrochemical reaction? Part C. What is the minimum molar flow rate of air required for the electrochemical reaction? Assume air is a mixture of 21% oxygen and 79% nitrogen by volume. What is the maximum molar flow rate of air delivered for the electrochemical reaction? What is the rate of water generation at cathode in grams per hour? The molecular weight of water is 18 gram per mole. We have a fuel cell whose capacity is to generate a 4 ampere current. Now, in order to generate 4 ampere current, what will be the minimum amount of hydrogen required? We know that in fuel cell, hydrogen and oxygen get consumed. So, in part A, we have to determine the molar flow rate of hydrogen and oxygen consumed. In part C, we have to determine the minimum molar flow rate required for electrochemical reaction. We use oxygen in order to supply, we use air to supply oxygen, because we know that air is free and we can supply oxygen from air, and we know that 21% of air is oxygen and 79% of air is nitrogen. So if air is used, so what will be the required rate of air in order to generate 4 ampere current from a fuel cell? What is the maximum flow rate of air delivered for the electrochemical reaction? In part E, we have to determine the rate of water generation at cathode. We know that in a fuel cell, water is produced, and from the overall electrochemical reaction equation, which is the global reaction equation, you can see that water is produced. So we have to determine the rate of water generation in gram per hour. Now, in part A, we have to determine the rate of hydrogen. So we have hydrogen as a species of interest. This is the 1 molar hydrogen, and it will be break down into 2 protons and 2 electrons. Now we will use Faraday law in order to determine the molar flow rate of hydrogen. Now we have a species of interest as hydrogen, and for hydrogen the value of N will be 2, because for 1 mole hydrogen 2 electrons are involved, so N will be 2 in case of hydrogen. We have discussed in a previous lecture that N is the number of electrons involved in 1 molar reaction. So in 1 mole hydrogen reaction, there will be 2 electrons involved, and F is the Faraday constant, I is the current generated from the fuel cell. So by just substituting I is equals to 4 ampere, N is equals to 2, this is the number of electrons involved in 1 molar hydrogen reaction, and F is Faraday constant, whose value is 96485. So by just substituting, the molar flow rate of hydrogen comes out to be 2.072 exponent minus 5 mole per second. This will be the minimum amount of hydrogen required in order to produce 4 ampere current. This will be the minimum amount of hydrogen required. Now, in part B, we have oxygen as a species of interest. So again, we will use the electrochemical reaction of oxygen. Now, closely look. For 1 mole oxygen, there will be 4 electrons involved, because here from this equation, in half mole reaction 2 electrons are involved. So in 1 mole oxygen 4 electrons will be involved. So for oxygen the value of N is equal to 4, and again the molar flow rate of oxygen will be determined by Faraday law, but for oxygen N is 4 because n is the number of electrons involved in 1 mole reaction. So for 1 mole of oxygen, there are 4 electrons involved in a reaction. So by just substituting I is equals to 4, n is equals to 4 and Faraday constant, the molar flow rate of oxygen comes out to be 1.036 exponent minus 5 mole per second. This will be the minimum amount of oxygen required for a particular fuel cell to generate a 4 ampere current. This will be the minimum amount of oxygen required. Now we have determined the minimum amount of hydrogen required in order to generate 4 ampere current, and we have determined the minimum amount of oxygen required in order to generate 4 ampere current from a fuel cell. Now in part C, we are using air to supply oxygen. So what will be the amount of air required? We know that air is 21% oxygen and 79% nitrogen by volume. So we can write the molar flow rate of oxygen is basically 0.21 of air or 21% of air. So the molar flow rate of air required will be nothing but the molar flow rate of oxygen divided by 0.21. We have determined the molar flow rate of oxygen in part B, and by just dividing the molar flow rate of oxygen by 0.21, the minimum amount of air required in order to generate 4 ampere current from a fuel cell will be 4.94 exponent minus 5 gram per mole. It means that if we supply minimum 4.94 exponent minus 5 gram per mole air, sorry, this is not gram per mole, it is mole per second. Here I have a mistake. It is not gram per mole, it is mole per second because we are talking about molar flow rate. So this will be the minimum amount of air required in order to produce 4 ampere current from a particular fuel cell. If we supply 4.94 exponent minus 5 mole per second air, then we are able to produce 4 ampere current from a fuel cell. Otherwise, it will not. Now in part D, we have to determine what will be the maximum reactant supply. So we have learned that there is no limit for maximum reactant supply. We can supply infinite amount of reactant for a particular electrochemical reaction, but it will just increase the parasitic power, while Faraday law only imposes a minimum amount of mass required. So there is no maximum limit for a reactant supply. In part E, we have to determine the amount of water generated. Water is produced from a electrochemical reaction in a fuel cell. When hydrogen and oxygen reacts electrochemically, it will produce water. So the molar flow rate of water produced will again be given by Faraday law, I over NF. I is 4 and F is Faraday constant. Now carefully look at the reaction equation which is written on your screen, that for 1 mole of water production, 2 electrons are involved. For water, there are 2 electrons are involved. So again for water, the value of N is 2. So by just substituting I is equals to 4, N is equals to 2, because for 1 mole of water generation 2 electrons are involved, and F to be Faraday constant, the molar flow rate of water comes out to be 2.072 exponent minus 5 mole per second. This is the molar flow rate of water produced. But in problem statement, we have to determine the mass flow rate of water in gram per hour. So we will convert molar flow rate into the mass flow rate by just multiplying the molar flow rate by the molecular weight of water. And we know that molecular weight of water is 18. We will use this formula written on your screen, that mass flow rate of water is nothing but the molar flow rate of water into molecular weight into 3600. We are multiplying by 3600 because we have to convert per second into gram per hour. So by just substituting molar flow rate to be 2.072 exponent minus 5 mole per second, molecular weight of water is 18. The mass flow rate of water is 1.34 gram per hour. So in 1 hour, 1.34 grams of water will be generated from a 4 ampere fuel cell. I hope that this problem is clear up to you. Now we are moving towards another problem. Consider a 20 cell stack operating steadily in series with 100 centimeter square active area per electrode with a current density of 0.8 ampere per centimeter square. The fuel cell nominal voltage is 0.6 volt per plate. A. Determine the water production in grams per hour for this stack. Part B. Determine the stack voltage and electrical power output. We have a 20 cell fuel cell. In fuel cell, normally we combine a particular cells to form a stack in order to increase the voltage, as we do in PV, as we do in solar cell. Similarly, we join fuel cells in series to form a fuel cell stack, as we join solar cell in series in order to increase the voltage. Similarly, in fuel cell, we join fuel cell to form a stack in order to increase the voltage. We have 20 cell fuel cell stack. There are 20 cells combined in series in order to form a fuel cell stack with 100 centimeter square active area per electrode. The active area of the electrode is 20 centimeter square, and the current density is 0.8 ampere per centimeter square. The fuel cell nominal voltage is 0.6 volt per plate. The voltage per plate is 0.6 volt. We have to determine the water production in grams per hour for this stack, and we have to determine the stack voltage and electrical power output. So first we will determine the current from a fuel cell, and it will be given by I is equals to IA, where small I is the current density and A is the active area per electrode. Current density is given to be 0.8 ampere per centimeter square, and active area is 100 centimeter square per electrode given in the problem statement. So for this fuel cell, the current is 80 ampere. It means that the 20 cell fuel cell stack is capable to produce 80 amperes current. Now we have current produced by a fuel cell. So we can determine the water produced from a fuel cell in grams per hour for this stack. We will simply use Faraday law in order to determine the water production. So the molar flow rate of hydrogen from one cell will be given by, this will be the molar flow rate of hydrogen from one cell, and it is given by Faraday law, I over NF. I is current from a fuel cell, N is the number of electrons involved in 1 molar water production, and F is the Faraday constant. The molar flow rate of hydrogen from one cell will be given by Faraday law. It is NH2O is equals to I over NF. Here I is the current generated from a fuel cell, and we have determined that from this particular fuel cell 80 amperes current will be generated. Small n is the number of electrons involved in 1 molar reaction, and F is the Faraday constant. Now we are looking at the electrochemical reaction equation for water generation, and from this equation we can see that for 1 mole water generation 2 electrons are involved. So for 1 mole water N is equal to 2, because for 1 mole water 2 electrons are involved in an electrochemical reaction. So by just substituting N is equals to 2, I is equals to 80, and Faraday constant is 96485. The molar flow rate of water required is 4.15 exponent minus 4 mole per second. This is the amount of water generated in mole per second. We have 20 cells. This is the amount of water generated from a one cell, but we have total 20 cells. So we will just multiply the water generated from one cell by 20. We will determine the amount of water generated from a 20 cell fuel stack. And molecular weight of water is 18. So the mass flow rate of water generated from this fuel cell stack is 538 grams per hour. Now we have determined what will be the amount of water generated from a fuel cell which is designed to produce 80 amperes current, and there are total 20 cells in a fuel cell stack. Now in part B we have to determine the power generated from a fuel cell. Since the plates are in series, we have seen in problem statement the plates of the fuel cells are assembled in series in order to increase the voltage. Voltage from the fuel cell stack will be N times V. When we join a cell in series, its voltage, total voltage will be increased, and total voltage will be the sum of individual cell voltages. So there are 20 number of cells, so N is 20, and each cell is producing 0.6 volt given in the problem statement. So the voltage from a fuel cell stack is 20 into 0.6, and the total voltage from a fuel cell stack is 12 volt. Now we have voltage from a fuel cell stack, and we have current from the fuel cell stack. So we can determine the power generated from a fuel cell by simply using a formula P is equals to VI. Here VT is the fuel cell voltage and I is the current generated from a fuel cell. Voltage from a fuel cell is determined to be 12 volt, and the current from a fuel cell is 80 ampere. So by just multiplying 12 into 80, the power generated is 960 watts. So basically 20 cell fuel cell stack is able to produce 960 watts of power, and it can produce 538 grams per hour of water, and it is able to produce 80 amperes of current and 12 volt of voltage. So if we go through this problem, we determine the molar flow rate of water by using the Faraday law, and then we determine the total water produced from a fuel cell stack in gram per hour by utilizing molecular weight. We have total 20 cells. Each cell is producing 4.15 exponent minus 4 mole per second water. That's why we utilize molar flow rate of we determine the mass flow rate of water in gram per hour, and then we have utilized the basic electricity concept, that if we combine cell in series, then it will increase the voltage. Each cell is producing 0.6 volt. There are total 20 cells, so total voltage from a fuel cell is 12 volt. And if we talk about the power from a fuel cell, power is nothing but the product of current and voltage. So by just multiplying current and voltage, the power from a fuel cell comes out to be 960 watt. Now with that, we have done with our lecture. If you have any query, any question related to this lecture, then you can ask in live session. You can also comment on Google Classroom. So this is all from my side. Thank you for watching this video.